Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started today, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on analytical challenges and solutions when using PlumeStop for in-situ groundwater remediation of chlorinated solvents. With that, I'd like to introduce our presenters for today. We are pleased to have with us Dr. Heather Lord, Environmental Research and Development Manager at Maxxam Analytics. In her current role, Dr. Lord brings new and improved service offerings to market aimed at reducing time and costs for fieldwork and lab analysis. She earned her PhD in analytical chemistry from the University of Waterloo and has published over 50 scientific research papers on the subject. Her areas of expertise include petroleum forensics and biomarker analysis, PFAS and related compounds testing, passive sampling in water, and development of new analytical technologies. We are also pleased to have with us today Rick McGregor, President of InSitu Remediation Services Ltd. Rick has over 26 years' experience in groundwater and soil assessment and remediation, has worked in over 30 countries, and has authored numerous papers on groundwater assessment and remediation. He holds a Master of Science degree from the University of Waterloo in hydrogeology and geochemistry, and is a certified groundwater professional in Canada and the United States. We're also pleased to have with us today Maureen Dooley, Director of Strategic Projects at Regenesis, who is on hand to answer any questions you might have related to PlumeStop. All right, that concludes our introduction. So now I'll hand things over to Heather Lord to get us started.
Thanks very much, Dane, and welcome to everybody on the line. I'm looking forward to spending some time with you over the next half hour or so, and then I'll pass it over to Rick to conclude the second half hour. So to start, I'll be, as you see on the slide, looking at chlorinated solvent remediation and specifically some of the challenges that we've seen in the lab and the solutions that we've brought to solve this. So first, an overview and just some background here. Of course, the in-situ application of carbon-based amendments for chlorinated solvent remediation has really developed strongly in the last decade, but of course it's not new. There's two stages that the current in-situ application uses, adsorption to the carbon and then degradation of the solvents in the subsurface. These two approaches, of course, have been used independently for quite some time. Adsorption has been used since the 1950s or so for ex-situ remediation, pump and treat type arrangements. And degradation in the subsurface has also had a couple of decades of in-situ use, bioaugmentation, bioremediation, that sort of thing. But what's going on here and what's new is these two stages are put together now, and then treatment, of course, in the subsurface. It is considered more effective than just subsurface degradation alone because the carbon will retard the movement of a plume and so stop the spread of that plume and then degrade it. So those are the features that are really helpful for this approach. Of course, there's a lot of carbon amendments available. So just to see where these colloidal carbons fit in the larger sphere of carbon-based products for remediation, of course, there's the Calgon products, the BOSS 100, BOSS 200, granular and powdered. Of course, they can be used with different additives, zero-valent iron, electron acceptors, or bacteria for bioremediation. And then, of course, different contaminants of concern, whether that's the VOCs with the granular product or the petroleum hydrocarbons with the powdered product, anaerobic or aerobic bioaugmentation. But then moving on, we then get into smaller particles, the granular or powdered Remington, similar targets, VOCs and PHCs. But then the PlumeStop is a different class. It's the colloidal carbon. So it's a very, very microscopic sized carbon particles. Of course, the smaller the particle, the larger the relative surface area. So it has a really nice feature that has got a huge surface area. Of course, if you're adsorbing stuff, more surface area is good. Again, it can be used for volatile organic carbons or petroleum hydrocarbons, or now it's certainly seeming like it's going to be a good product for PFAS remediation. And as I mentioned, there are the biodegradation as well that's injected with it. There's also another colloidal product that is probably in a more of a research stage. It's not commercially available right now, but so this topic is all on the PlumeStop colloidal carbon. So just a quick overview of what the field process looks like, and Rick will follow along and enhance this end of the talk significantly more. I'm just going to touch on it briefly here. So typically what you do is you'd start out with some pre-injection subsurface characterization. Get to understand the magnitude of plume and the amount of carbon or organic carbon to be treated. And then from that, you will select your loading rate just to make sure that you're providing sufficient contact between the carbon amendment and your contaminant in the subsurface. Of course, then you need to do an injection. The colloidal carbon is particularly good for high permeability formations using either direct push or injection wells. The larger powdered and granular are more often used with low permeability formations. And then after injection, sometimes there is an interest on characterizing the distribution of the amendment by soil coring, or quite often actually that step is not done, but it is possible to do that if you need to verify the distribution of the colloidal carbon in the subsurface after injection. Now, to move on to the more lab-based part of this talk, when we first started seeing these samples in the lab, we realized that there were some analytical challenges with these samples when we put them through our standard analysis. So I'm just going to run through what some of those were. So in the field, it's important that you monitor the contaminants in a separate monitoring well from where you did the injection. That's to make sure that you're not pulling actually carbon out of the location that you put it into. But sometimes in these monitoring wells, you're still seeing some of the amendment come out in the water when you're sampling, particularly if you're sampling soon after injection, before the carbon has had a chance to settle in the subsurface. Of course, there might be need to do this. For instance, if you're doing a property transaction, you might not want to have to wait until that carbon settles out to know that you've done sufficient loading of the PlumeStop to sequester that plume move. So there are other reasons you might need to do the sampling earlier, and in some cases you may get carbon coming out in the samples. So this slide you see, the picture you see on the bottom right here, these are two samples that we received in the lab, both with PlumeStop in them. The one on the left settled quite quickly after we received it. We prefer to draw our sample for analysis from that top clear part and avoid getting the carbon in the sample that we take for analysis. But of course, if you've got a vial like the one on the right that it sat for a couple of weeks or longer and did not settle, then we have no choice but to sample with some of the carbon in the sample. So yes, we try to allow the carbon to settle prior to analysis wherever possible. But particularly for those samples that, for whatever reason, the carbon doesn't settle in the holding time, we have to analyze it with the carbon in it, and then we can get into some challenges. So just a very brief slide here on the lab processes so that you can understand a little bit where these complications come from. So on the left of this slide, you'll see a sample here, a sample vial. What happens with that sample when we bring it in? As I said, we draw a bit off of the top to try to avoid that carbon as much as possible. Then we put it into a vial with a headspace in it because we are drawing out a sample of the headspace, that is the air in the top of the vial, for analysis. We mix the sample, however, with this solution. It's a salt solution called matrix modifying solution. Very technical, of course. Anyway, what the salt does is it pushes the volatile organics into the headspace of that vial so that they're more easily measured to low detection limits. But at the same time, we also add some laboratory standards. So on the left, you'll see internal standards. Those are added to allow us to do calibration. And then on the right, you'll see that we also add something called recovery surrogates. They monitor to make sure we're getting good recovery from every sample. And if we're not getting good recovery, we know that we can't report because it's not going to comply with our quality systems that require good recovery. So once this sample is all mixed together, then you can see on the right, there's some things that go on in this sample, particularly if there's a significant amount of carbon in it. So just like the carbon sticks to, or the chlorinated solvents stick to the carbon very well in the subsurface, they will also stick to the carbon in the sample vial. This is mostly a problem for the internal standards and the recovery surrogates. Because if those lab standards stick to the carbon very tightly, and they are analogs of chlorinated solvents, so they will behave just like the chlorinated solvents in the subsurface, then you would get a poor recovery in the sample or in the analysis, and then we wouldn't be able to report it. So unfortunately, what happens if this is the case is we have to dilute these samples quite significantly in order that those internal standards and recovery surrogates are recovered with the appropriate efficiency. But when you dilute a sample a whole lot, the detection limit goes up. And unfortunately, sometimes we have to dilute the sample so much that the detection limit is no longer useful if you're trying to meet a specific criteria. And you'll see how this affected a couple of projects that we worked on. So there's two sites that I'm going to describe. So site one here, I'll just tell you a little bit about it first. This was a low concentration chlorinated solvent site. Vinyl chloride was the contaminant of concern. It was a remnant after 15 years of air sparging, pump and treat, vapor extraction, and such. It had been present at the site on the order of 10 micrograms per liter for quite a while, and so the client was looking at using PlumeStop to do a polishing to try to get this vinyl chloride down below the site condition standard, which in this case was 1.7 micrograms per liter. So just a small amount of carbon was injected, 230 kilograms, and monitoring did start 1 month after injection because, as I said, this was a property transaction where they wanted to get an early indication that the contaminant was being sequestered and remediated so that the property transaction could go through. They did use low flow sampling, but unfortunately that wasn't quite enough, and there were complications with the analysis. Site number 2, on the other hand, was a very high concentration, again, vinyl chloride site. 6,000 micrograms per liter was on site. And PlumeStop was used as a first try to get this site remediated. So there was a much higher carbon amount injected, 2,500 kilograms. Again, trying to meet the site condition standard of 1.7 micrograms per liter. The first sampling was done 3 months post-injection, And again, the liquid activated carbon concentration was too high in most of the samples to allow direct analysis of those chlorinated solvents without having to increase the detection limit far above that 1.7 microgram per liter limit. In this site, we looked at passive diffusion bags, monitoring both pre and post injection in order to understand what that chlorinated solvent concentration was in the water without seeing the interference of the PlumeStop. And I'll describe how that worked in the upcoming slides. But first, I'm going to show you a little bit about what the problems were when we just tried to analyze these low-flow samples by standard analysis. So on this slide, what I'm showing you is months after injection on the x-axis, and then the vinyl chloride concentration that we monitored by our standard analysis with those internal standards and surrogates from those samples. And again, we did try to decant just the top, the clear portion, trying to avoid the carbon wherever possible. So you'll see at 1 month in, we were getting about 10 micrograms per liter found. But you'll see the small red dashed line down at the bottom left by the 2 microgram per liter concentration, that was the detection limit of this analysis, because we did have to dilute that sample 10 times in order for those surrogates and internals to pass. You'll see that that is above the guideline of 1.7. So this was not helpful for the client, because if they did get a non-detect, they wouldn't know if it was actually non-detect below the guideline or not. And actually the next sampling at 4 months was non-detect with a detection limit again of 2, because they had to do that 10 times dilution again to get the quality control to pass. Then at month 5, they sampled again. This time there had to be even a larger dilution. The detection limit was 4. The concentration's coming down. It's now about 6.5, but a detection limit of 4, so that's still not helpful. However, after 8 months, the concentration did get down reproducibly below the detection limit. And you can see there that the 3 samplings in a row verified remedial success, but it took 8 months to know that this was happening. So we really wanted to get a solution for this. So first thing we did was we tried to figure out how much PlumeStop in a sample is going to cause a problem with the analysis. So we set up a bunch of trials and saw what loaded various amounts of PlumeStop in order to then start to understand exactly how much PlumeStop does cause this problem with analysis. So you can see here what these vials looked like between 10 and 180 milligrams per liter of PlumeStop. And spoiler alert, 100 is the magic number. And you'll see that in the next slides. So you'll see that 100 milligrams per liter is probably a fairly dark sample, but you're probably still going to be able to see through it a little bit. More than that, and it's going to be almost impossible to see through it. So that's a good cue in the field, that if your sample is so black that you can't see through it, it's probably going to fail. If you can see through it, it's probably going to pass and we'll be able to do the regular analysis. So that's I think, a helpful hint for field crews. So let's look at what happened for different concentrations of carbon with these surrogates and internal standards that caused us to have to fail the analysis and dilute the samples. So you'll see on the left is results from site 1, the low concentration vinyl chloride site with a low amount of carbon loaded. And then on the right, we've got site 2 with the higher amount of carbon and the higher levels of vinyl chloride. So on the left, you can see that at carbon loadings up to about, those samples were all around between 10 and 50 milligrams per liter of PlumeStop. And the points on this graph are our internal standards and surrogates, and they're all between the dashed lines, so they passed. Out on the right, once we're up to about 175, 180 milligrams per liter, now the surrogates and internal standards are moving out towards those dashed lines, and some of those samples will fail. Then on the other side of this coin, site number 2, you can see much higher carbon loading in these samples, up to 3,000 milligrams per liter. And again, the samples with very low carbon, those surrogates all passed. The ones over about 700, 800 milligrams per liter were clearly failing. So between these two, we're pretty confident in saying, yes, it's about that 100 milligrams per liter where we start to have problems. And you have to think about an alternate approach. This is the other set of standards that we put in. And these are the internals, and you'll see that again it was about that 100 milligrams per liter that in this case the results came back below the dashed line, which is our acceptance criteria. So again, confirming that 100 milligrams per liter is where we start to see problems. So the solutions that we came up with, the first thing we did was change the way we do the calibration. Just to verify that it was the problem with the calibration that was giving us a headache. So we did something called external standard calibration. Basically, we ignore the internal standards. You're not allowed to do this to report it, but we just wanted to try it. And yes, if we calibrated by ignoring those internal standards, it worked fine. The second approach was, as I said, the passive diffusion bag sampling. So here's a slide to describe what passive diffusion bags are and how they work for people who perhaps haven't seen them before. What it is really just a sausage of polyethylene tubing filled with clean water. And then you'll see a picture of it to the right, these two photos at the right. There is also a black mesh on the outside of this polyethylene tube just to give it some abrasion resistance. The tube is put into a groundwater monitoring well, left to equilibrate for a week or two, and then once the passive diffusion bag is removed, you can see the picture in the middle. They're transferring the water from the passive diffusion bag to a regular volatile vial for submission to the lab. Of course, in the subsurface, while these things are equilibrating, the carbon can't move into the polyethylene, but the chlorinated solvents can. So once this has equilibrated after that 7 to 14 days, the water concentration inside the bag is the same as the water concentration outside, but there is no carbon inside the bag. So then we can get an accurate measure of what the free water concentration was without having to dilute. So we went back and took a look at some of these sites that we had looked at previously. So this is site 1. You've seen this chart before, but this time I'm showing you both the external standard results at month 1 and the passive diffusion bag results at months 4 and 5. And they were giving us very similar numbers. We knew the external standard calibration was going to work properly because it wasn't going to be affected by the carbon. And we were happy to see that the passive diffusion bags were giving us similar numbers, so we knew that it was working. So on site 1, here's some further data. These are 3 different monitoring wells. The blue bars are low flow. The red bars are passive diffusion bags, and then the triangles show where the detection limits were for each of these. So you'll see that for monitoring well 2 and monitoring well 3, fairly high carbon loading, and the low flow detection limits were elevated, whereas the passive diffusion bag detection limits were not. And again, if we look at our internal standards, on the right you see all of the internal standards pass with the passive diffusion bag. That's expected because there's no carbon, whereas they're failing on the left with the low flow analysis. Here's site 2, comparing the passive diffusion bag results again versus low flow. So passive diffusion bag on the left, low flow on the right. And again, you'll see that we're actually getting some very comparable results. You can see in monitoring well C, those results are very comparable. Week 1 and 1 week pre and 3 month post. And on monitoring well B, it's also quite similar. Monitoring well A, that's showing us that the remediation is working. So 1 week pre, we've got 10,000 micrograms per liter. 3 month post, the passive diffusion bag results are telling us we're now down to about 5 or so micrograms per liter. So we can say, yes, the remediation is progressing. No, we can't do a standard analysis, but at least we know at 3 months how this is working. And then that site 2 again, we went back a little bit later, 5 months post, 6 months post, 1 year post. The first 3 bars are low flow analysis, and there was liquid activated carbon still observed in those wells. 6 months post, that was a passive diffusion bag analysis, so good detection limits. We were getting the same results as we did with low flow. So again, we know that the passive diffusion bags are giving similar results to low flow, just those lower detection limits. You might ask, why is there still vinyl chloride on this site? We figured what was happening here is it's being generated due to degradation of the precursors TCE and DCA. However, 1 year post, we were getting not detected in the passive diffusion bag, and it was success at that point. So some conclusions here. We have found that on these sites where you have to sample with high levels of liquid activated carbon in the sample, in order to avoid these problems with the interference with the lab analysis, the passive diffusion bags are working. And this works at both high and low concentration chlorinated solvent sites. Now, you should be aware that the passive diffusion bag is only reporting the freely dissolved concentration. It doesn't tell you what's still on the carbon, but it does tell you how much chlorinated solvent is still freely dissolved in the water and able to migrate. However, once the carbon finally does settle out, we have shown that the passive diffusion bag and standard analyses produce the same results. So with that, I thank you for your attention, and I'm going to pass it over to Rick now, and he's going to talk more about the field application of liquid activated carbon.
Somebody asked about how long do we typically wait between the injection and our first sampling. What we usually with PlumeStop type applications, generally people want to look for results pretty quickly, so 1 month is typical. So it is possible in that time frame that you may have some of the PlumeStop still present. It hasn't completely sorbed to the soil and the colloid hasn't completely broken. So that's why some of the information that Dr. Lord was presenting is, I think, can be useful. So 1 month, can be pretty typical for that first sampling event.
Thanks, Maureen. Getting a lot of questions coming in from the audience.
Okay, 1, if the sample has less than 100 milligrams per liter, do the analytical results indicate what's actually in the sample and not eluting from the carbon particles? So I think one of the things that I know that they were looking at the lab, if you have some transparency through the sample itself, it's usually below 100 parts per million and in that range. I think I'll wait for Heather to maybe chime in on this, but at that level, I mean, I think you still have a little potential for some cross interference, but I mean, you're going to have some of the sorbed material still on the carbon. So there still is a little bit of a chance for some interference. And I think where it's really particularly important is if you're looking at samples where if it's a petroleum hydrocarbon and if it's an extraction, you're absolutely going to see some, the results of some of those samples in your analyses. So I think that's something to really look at. So it, theoretically, if it's a headspace, with the carbon, you shouldn't have as much interference, less than that 100 ppm. But I still think you have the possibility of having some of the solvent, sorbed on that sample, and could have a little bit of, cross interference.
We have a lot of questions coming through, so maybe
yeah, one of them was about clay, the application of liquid activated carbon in clay. Here's the thing. So anytime you're injecting this like water, are you going to push it into a really, really fine grained material? That might have its own challenges. I said, but where PlumeStop or liquid activated carbon, because there was a comment that Heather had made about, reduced soils with reduced permeability. We certainly use liquid activated carbon in those settings. What tends to happen is you're going to set up the carbon at the interface between the more permeable and less permeable zones, and that allows you to manage any back diffusion because the ability to get this injected and through the formation because of the size. So to answer your question, we're going to take a good look at something that's clay. Is it, how might, where is the contamination? Is there some other, way to inject to get it so you can get to where the contamination is and try to manage that back diffusion? But clearly we would work pretty closely with you to see if that's something that's, that's feasible and if we can get the material applied. Mark had a question up here. The question is about, is 100 ppm lab QA/QC for suspended concentration threshold before or after allowing the solids to settle? I mean, I would assume it would be after the solids settled if you could decant that part of it. But, sometimes with the PlumeStop, it doesn't settle really well, and I know people are asking about centrifuging, and it just doesn't centrifuge that well. There are some techniques where you can use like a calcium chloride to break the emulsion and help settle it. So that gets into the integrity of doing a VOC sample, but that's one of the other techniques that can be used to try to break that emulsion.
I'm going to talk about a site here that was done in metropolitan Toronto. It was a low mass chlorinated hydrocarbon plume that we used PlumeStop as well as the added electron donor, in this case HRC, to remediate the site. The site was, various options were considered by the consultant and us, including this long list of options typical for in-situ. They wanted to do in-situ at the site because it was mostly underneath a building, and the building was actually sold, and part of the transaction was due on completion of the remediation. So of course, with any in-situ program, we're always concerned about first distribution, as well as the sensitivity to back diffusion, matrix diffusion, and as well as, in this case, we're looking at some of the chlorinates, which have very low regulatory standards here in Ontario, including things like vinyl chloride, which is either 1.7 or 0.5 parts per billion. So we won't get too much in the activated carbon. Maureen and Heather give you some background on it, but from our point of view as being applicators, we're really concerned about basically how well it goes in the ground and the distribution of the activated carbon once it's in the ground. If you don't get distribution, then you're pretty much game's over from an in-situ point of view. Also, from an activated carbon point of view, we're always concerned about the lifespan, how it will behave, because activated carbon will absorb anything that's organic or even some heavy metals, and therefore if it has a higher affinity for the carbon, then something that's being absorbed to it can in theory be desorbed from it. So something like a benzene can be desorbed relatively easily if something no more preferential like a PAH or a PCB or something heavier comes along. So Heather alluded to this earlier. Generally speaking, when it comes to activated carbon, the smaller the grain size, the more absorption sites it has, just due to the surface area. So in theory, this is a study done by Tom Higgins and colleagues at Colorado, who looked at some of the grain size. Now these were, they're looking at the PFAS for PFO and PFOS. But in general, what you see if you really look at these graphs in your spare time, you'll see that as the grain size decreases with the activated carbon, the better and faster absorption will happen. And this is generally true of most organic compounds. So why do we choose colloidal or a PlumeStop at this site? Well, it's been relatively well demonstrated now. We've used probably over 40 sites in Canada now. You see 3 of them today. Worldwide, I'm sure it's well over 200 now worldwide. And we like it just because it goes into the ground in what I call injectability. It goes in the ground really easily. It's almost like water going in the ground. So we don't have to worry about it like we have to worry about more viscous compounds like some of the oxidants or some of the bio remediation compounds. It's small, so it can be transported. Now, one of the things that it can be transported on injection, but it does settle out. There are some issues, concerns with people saying that it might be transported for meters or lots of feet. That's just not in our experience happening. We see it maybe typically go 3 to 5 meters and then it settles out. So so it's good for injection, but it does settle out with time. The other things that our clients like is it's usually a one-time application, unlike most oxidants, and it's generally less disruptive. This is micro photographs from courtesy of Regenesis, just showing scanning electron microscopy of quartz sand grains before and after the application of PlumeStop. So you can actually see in the photograph on the right how fine and how small the colloidal activated carbon is here compared to a sand grain. But it actually, you can see how well it coats the sand grain too. This is from another site. This wasn't done at this site, but this is another site where we actually did a side-by-side comparison of a powdered activated carbon against the liquid or colloidal activated carbon. And we wanted to look at the distribution. And 2 things we wanted to look at was the distance from the injection point, as well as how well it went into the zone of what we call the target zone. And the target zone here is identified in each graph by the dotted lines at about 1.7 and 2.1 meters below ground. That's where our contamination was focused, and that's where we wanted the reagent to go. So we did a study here where we did detailed vertical analysis of activated carbon within the soil. You can see here that the powdered activated carbon was very focused, basically at one level, about 1.9 meters below ground in the bottom graphs. And we've seen it about 7 meters away from the point of injection, where upon the colloidal, we've seen it more dispersed over the 1.7 to about 2.1 meters, which is, and we also seen it detected out to about 7 meters. We prefer the top graph just because we see more distribution over the whole zone of influence, whereupon the bottom zone, we've seen it mostly go into, and that one point where we detected that was correspond to about a 1 to 2 order of magnitude higher hydraulic conductivity sandy seam within the till material. So we'll get to the site here. So it was an industrial facility, and it had low-level chlorinated solvents. So it wasn't a high mass zone, but it was widespread over about almost 1,000 square meters underneath the building. And time was of the essence because a real estate transaction was. You can see from the photograph here, we had residential on the right side of the screen, light commercial, industrial above and below the site, and to the west of the site, we had a railway facility. So all sorts of mixes. The geology was a sandy fill overlying a silty till. We had some sand lenses present, and our hydrogeology, water table was about 3.7 or about 11 feet below surface, unconfined aquifer, a fairly high hydraulic conductivity, but our gradient was fairly low, and it resulted in a low, about 3 centimeters per day or 1 inch per day groundwater velocity. It was a carbonate buffered aquifer. We had no nitrate or oxygen present, iron sulfate reducing, which is typical of these plumes. Since it was in an industrial, in an urban area, we did have some salt present in the groundwater. We looked at these options, a whole suite of options. We zoomed in at the end on looking at enhanced anaerobic bioremediation, as well as the absorption technologies. We ruled out, at the end of the day, we ruled out the anaerobic because one was the time frame involved. The 2 was some of the concern about the generation of vinyl chloride at the site. So we zoomed in on using the PlumeStop, the liquid activated carbon, along with enhancing it with some hydrogen releasing compound, which is shown in this slide. This just gives you sort of the properties. You can look this up on the Regenesis. These are both Regenesis projects, so I'll let you look these up on the websites if you want further details. But fairly, the HRC's been around for quite a few years now, so it's quite well proven and well used. And the PlumeStop itself is starting to get a pretty good database of performance. So how we injected it? We assumed a 0.3 pore volume method. We used direct push or geoprobe with specific tools. We did it at multiple locations, multiple vertical intervals to make sure we got good vertical and lateral distribution. Low pressure, our highest point was 75 psi, and we put in about 450 liters of solution at each interval. So overall, we injected about 16,500 kilograms of PlumeStop, almost 500 kilograms of hydrogen-releasing compound, which was contained about 100,000 liters of water. We injected 90 locations over 900 square meters, and once again, these are the pressures. And it was completed over a 4-week period. Of course, from a everybody worries about budgets. From a budget point of view, we looked at it 2 ways. One was by timing, so we were 2 weeks under budget, 1 to 2 weeks under budget, and we had very minimum waste loss of reagent, which is very important because reagent is money. So we had less than 1% of the, so we had 1 point that daylighted basically, and that resulted in less than 0.05% of the solution lost. And the money budget was 5.6% under budget, so we came in under budget. Distribution, so we did 4 cores, just randomly cores across the site to make sure we got the reagents within the zone of influence, our zone of impacts. So our zone of impact were about 3.6 to 6.8, 6.9 meters below ground, and we did 4 cores over the whole area, and we just looked at it, and as you can see here, we were able to target the areas, and we usually got 3 to 5 times more activated carbon in those areas than we did in the zones that we weren't targeting. So the results of the study was, so this for the distribution, which is probably the most important part, is 43 of the 44 samples we took were within the zone of that we were targeting. So that was excellent. We had a mean of 0.32 grams per kilogram in that zone, whereupon the background of the soil that we weren't targeting was less than 0.1 grams per kilogram. So that's detection limit in this case. We had 2 samples outside our target zone that we actually detected liquid activated carbon. So basically everything we injected went where we wanted it to. So that was a very good key, and that's probably what set up the success of the next point, which was the actual analysis. So they did analysis at 6 weeks, 6 months, and 9 months. So it's at all times they did not have any detection of any of the chlorinateds, which were in this case PCE, TCE, cis, and vinyl chloride. We did have PlumeStop within the samples after 6 weeks, which is very common, and Heather talked about this. So there was some laboratory challenges with that. So the detection, the analysis were, I don't want to say suspect, but they were qualified as Heather talked about earlier. But at 6 months and 9 months, the PlumeStop had settled out, and we showed that basically the regular sampling using low flow sampling came back with non-detect samples for those. At a couple of other wells, we did have heavy metals, including cadmium, detected. The activated carbon was actually very effective at removing that, so we never detected cadmium afterwards. And at one well, we did have petroleum hydrocarbons present, and the activated carbon once again did a nice job on removing those, and we haven't detected those since injection. So that's kind of a zipped up version of it, but hopefully that leaves some time for some questions in that for everyone.
Okay, great. Thank you very much, Rick. Yeah, so we do have some time left for questions. Just really quickly before we get into our questions, just a couple of reminders. First, you're going to receive a follow-up email with a brief survey. And also, after the webinar, you will receive a link to the recording as soon as it is available. We do have a lot of questions coming in here, so if we do run out of time, before we're able to get to your question, we'll follow up with you after the webinar. All right, so we got several questions for Heather. Is Heather available? Does Heather have audio or?
Can you hear me? I'm
okay,
available
great.
here.
Yep, great. Okay, awesome. Yeah, so let's see here. A question for you, Heather, is why not filter carbon out of a water sample?
Well, there's 2 problems there. First of all, the colloidal carbon is very, very small. It goes through everything down to a 0.2 micron filter, and even some will come through a 0.2 micron filter. The other problem is the filters clog almost immediately. So it's very difficult to filter, but the more significant problem is that any filtration process will cause significant loss of volatiles. So it's not possible to filter and maintain the same level of volatiles that were in that sample when it was submitted.
Sorry, here's another question for you, Heather. Could a centrifuge be used to reduce the amount of suspended liquid activated carbon from the VOC vials?
Yes and no, but mostly no. Again, because of the extremely small size of the colloidal carbon, you need a very high-speed centrifuge to centrifuge that out. Such centrifuges are available in some university labs. But certainly it's not routine for any environmental labs. But second, as with filtration, centrifugation also causes loss of volatiles from the sample. So yes, the 2 points. The typical environmental lab centrifuges that are normally used for centrifuging, for instance, sediment out of a sample, simply don't spin fast enough to sediment the colloidal carbon out of a sample. And second of all, the centrifugation causes loss of those volatiles from the sample.
Okay, great. All right, so let's see. Here's another question for you, Heather. Would you apply the routine VOC 7 or 14-day hold time for samples with visible carbon?
Well, the protocols here in Canada allow us for a 14-day hold time. I think if it hasn't settled out within 7 days, the chance of it settling out in 14 is relatively low in our experience. It normally will settle out in, like, either it settles out immediately or perhaps 3 to 5 days, or else it just doesn't settle for weeks, or if at all. So I think a 7-day hold time will normally be fine. If it's going to settle out, it will have by then. But here certainly in Ontario, we are allowed a 14-day hold time.
All right, great. Let's see here. Here's another question for you, Heather. And the question is, how long do you typically wait for equilibrium with the passive diffusion bag before collecting your sample?
I recommend 14 days. Probably most of the chlorinated solvents have equilibrated within 7 days, but 14 days gives much more confidence.
Okay, follow up on another question related to the passive diffusion bag, and that is, can you use the passive diffusion bag in a 1-inch diameter monitoring well?
Yes, you can. There are two, for the supplier that we use, which is EON out of the States, they sell these bags in 2 different diameters, a 1.75-inch diameter bag that will go in a standard 2-inch monitoring well, or they also have a 3/4-inch skinny passive diffusion bag that will go in a 1-inch monitoring well, and we've used both. Now, you just have to be aware with the skinny passive diffusion bag, you may not be able to get enough water recovered from it to fill 3 standard 40 ml VOA vials. So you just have to be careful about that, but you can get them longer.
Okay, great. Another question related to the passive diffusion bag, and that is, how can it be verified that the distilled water within the passive diffusion bag is not present in the retrieved sample, effectively diluting the contaminated water?
No, I think there's perhaps a misconception. What happens is the chlorinated solvents that are in the water in the groundwater well move through the polyethylene into the distilled water inside of the bag. So the distilled water is not going to dilute the water in the well. But what happens is after that 7 to 14 days, if you started out with, say, 10 micrograms per liter in the freely dissolved in the well, you will end up with the same 10 micrograms per liter inside the bag. So the only time that you would have a problem with so-called a dilution effect would be if you took that passive diffusion bag out in like 3 or 5 days when it had not fully equilibrated. Then you would get a low bias. But as long as it's equilibrated, there will be no low bias, and the concentration inside the bag will be the same as the concentration outside. Now, does that answer the question sufficiently?
I think so. Excuse me. I think so. Getting lots of questions here. Some questions also for Rick McGregor. Rick, here's a question, and it is: can liquid activated carbon be used in a fractured bedrock environment?
Yes, we've actually did quite a few sites now on fractured rock, and it really behaves the same way. You basically coat the fractures, which is good from both the fracture, the flow through the fracture, as well as back diffusion from the rock matrix itself. One of the things you may be a little concerned about, obviously in fractures, you will get bigger radius of influence most likely. So you may, in some cases, want to inject a calcium chloride solution afterwards to drop out the PlumeStop if you only have to treat a small area. But yes, we've applied it and it's worked quite well in fractured rock.
Okay, great. Another question for you, Rick, and that is advantages over Boss 100 ?
Well, I don't want to get into comparing products. They both have their advantages, disadvantages. Generally speaking, the PlumeStop is it's not generally. It is a smaller diameter. So from an injection point of view, it generally goes into the ground at lower pressures. Whereupon when you're talking granular or powdered activated carbon, you generally need higher pressures to go in, and sometimes you need to fracture the subsurface to get them in the ground. So that's one of our, from an application point of view, that's one of our biggest considerations. The other one too is just the size of the particles themselves. As Heather started discussing, there's lots of papers out there that talk about the surface area of activated carbon generally gets smaller. I mean, their surface area gets larger as the particle size gets smaller on a relative basis. So in general, when you're looking at absorption, you want bigger surface areas. So those are two of the things to consider. But once again, it comes down to the geology of a site and your what you want to do with the site. So hopefully that answers the question.
All right. Thank you, Rick. Let's see here. We're getting a couple of questions also, some additional questions about PlumeStop. This one is for you, Maureen, if you could answer this one. And the question is, does PlumeStop have a corrosive character, or does it compromise a pipeline as you would see with, or as with a persulfate injection?
Yeah, the answer is no. The PlumeStop itself, it has a little bit of, it's a little bit alkaline, but it's not corrosive in any manner, so we can apply it near a lot of sensitive infrastructure.
All right, thanks, Maureen. More questions here. We do have maybe time for one or two more questions. This is one for you, Rick. The question is, for this industrial site, was the injection depth targeted to the sand layer zone, or was it within the till zone?
It was within the till zone. Now, the till zone did have some sand seams in it, so that's why we did the distribution cores afterwards to make sure everything was distributed through the till, which was a silty material, as well as through the sand seams. So we wanted to make sure we just weren't injecting into the sand seams. So, but it was in the till itself.
All right. Another question here for Rick. Rick, what was the approximate cost for this injection program?
Overall, for everything, for the not excluding the monitoring, which is done by an independent consultant, it was about $200,000. That's Canadian, so whatever that is in American, $20,000 or so in American, or I'm just joking about that, but about $200,000 Canadian.
All right. Okay, well, thank you very much, Rick. Thank you, Heather. Thanks, Maureen. We are out of time, so that's going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. Thanks for staying with us through our audio issues. If you would like more information about analytical services from Maxxam Analytics, please visit maxxam.ca. If you'd like more information about remediation services from IRSL, please visit irsl.ca. And if you'd like assistance with a remediation solution from Regenesis, please visit regenesis.com to find your local technical representative, and they'll be happy to speak with you. Thanks again to Dr. Heather Lord, Rick McGregor, and Maureen Dooley, and thanks to everyone who could join us. Have a great day.